This is Chapter 17, Water Resources, Lecture 2. So picking up here, all right, how do we study groundwater? Well, you can do field studies to look at the sequence and character of rocks that actually hold groundwater. Geophysical surveys can be done as well. We need to know the depth to bedrock and to water in the saturated zone, the aquifer. Drilling can also be used to verify geology, the depth to water, and provide water samples or pump tests. Look at how fast we can pump out water from the subsurface as well. We can measure discharge, losses and gains of water, and water quality from the surface. We can also depict the water table in a few standard ways. So what we have here, through various measurements, probably well data, these numbers show elevations of the water table. We want to know what is the pattern, from this map. Which way do you think it would flow? Well, just the same way you draw a contour map for lines of equal elevation, you can do that for a water table based on well data measurements. So this water table has lines of equal groundwater elevation. We see blue arrows showing the flow, which is, say, down slope, down gradient, and groundwater is flowing to the south, roughly here. You can compare the water table to other features, such as land use, to ask, is there something in this landscape that might be impacting the groundwater table? Is there a lot of activity down here that's making it lower, or is it a geologic feature that makes the water table what it is in this area? And with that, we do think about overpumping of groundwater from a well. Okay, so this is a water table before it was overpumped. And overpumping is basically pumping more water out than can recharge to maintain this water table. So before overpumping, the water table is fairly flat. Water flows to the left past a small well. But then someone puts a large well in here that can pump a lot of water out. Okay, and a large well causes a cone of depression, we call this, to form in the water table, like a sump, a low area. Okay, so water cannot flow fast enough into this area to replenish the amount of water that's withdrawn from the well. So in many cone of depression situations, the water table becomes steeper near the well because the water's withdrawn too fast. So in this smaller well, it looks like the water table's going up, when really it's just a cone of depression. And with overpumping, we can also have land subsidence, meaning the land drops down because the water table drops, the aquifer compacts, and land subsides with it. Okay. Fissures can also form along boundaries between areas of more and less subsidence. So there's more subsidence over here and less over here. Along a coast, fresh water floats on salt water. So if you overpump an area like this, you remove the fresh water too fast, salt water can come in and contaminate that aquifer. This has happened before, say on a small island community, large company comes in, uses up a bunch of fresh water and contaminates the formerly good usable aquifer. This is why it matters to know what overpumping is in an area, like how much water can be taken out of an aquifer without negatively impacting it. This is how I spend most of my week, is looking at groundwater contamination. This area has a lot of things that could be impacting the aquifer that we see below here. So how can the water become contaminated here? We'll identify all possible sources. And there's a few. Okay, so this is like a mining area. So this is naturally mineralized rock. It has some things in it, perhaps, that we don't want in our surface water, which can flow into groundwater. So this is pretty irresponsible to have that right along the banks of a river. This is a landfill. I work with landfills a lot. They are lined and monitored with wells around them. New construction landfills are, of course. But they are a risk to groundwater, and that's why they're monitored and regulated. This septic tank. Okay, so when you're not, say, on the grid with a sewer system, you have a septic tank, and all of your wastewater from your home flows into that, and it discharges to the subsurface. And it's not treated or cleaned, so it could potentially contaminate an aquifer. That's why there's some setbacks from a drinking water well that have to exist. And that's why drinking water wells are supposed to be much deeper than the upper aquifer, if possible. Farms, sure, there's a lot of things from farms that could impact water just because you're dealing with nutrient loading to yield crops. Leaking tanks and gas stations. In the last 100 years, this has been a big issue, and a lot of leaking storage tanks have been cleaned up thanks to basically taxpayer money. All right, trucks, this happens all the time. They crash, fuel can be spilled, so there needs to be a response quickly to install booms or barriers around this spill and get it cleaned up before it impacts the aquifer. Dry cleaners also historically many of them dumped their chemicals like right outside, so impacted aquifers in the areas where they existed. Households, I mean, anything can happen in a household. If you don't feel like recycling your used oil, what do? Hopefully you do recycle it, but people, of course, have historically dumped household chemicals outside, which is bad because it impacts our water. Or, whatever happened upstream can be brought by the stream to other areas. Oh, we've got a metal recycler here too. Factories can release things from their processes that impact our water. Fuel storage tanks as well, if they're leaking, that's a problem. And I was going to say too, contamination from other areas not pictured in that area can be transported through groundwater flow. So, how does groundwater contamination move? And I've been so general with groundwater contamination, but it's anything that can impact the health of living things. Okay, like arsenic, PFAS, volatile organic compounds, any other kind of heavy metals, too much salt. We're calling all of that contamination. We can't drink it, Okay, so contamination largely moves with groundwater down the slope of the water table. It can be, say, naturally filtered out with enough time. If you've got groundwater flow that's very slow and in contact with material like sand, sure, that's a nice thought. But it's not filtered out if flow is rapid, like through limestone caves. We need to know the direction of groundwater flow. That's very important in the cases of groundwater contamination, because we need to know where those contaminants are moving. And we can use the flow direction to figure out where the contamination originated to begin with. So how do we track and remediate groundwater contamination? So in this case, you have some kind of contamination plume from this building right here. Maybe it's an oil spill, okay? Groundwater is flowing toward us in this direction. It spreads out due to diffusion and mixing, and it forms a contamination plume. What we can do then is figure out the extent of it. After we identify that there was a contamination incident, we need to know the extent of it. So look at a groundwater contour map, develop one if one does not exist. Look at groundwater flow direction and velocity, and then kind of delineate the extent of the plume. After that, say we could drill wells to intercept that plume and then pump out that contaminated water and treat it at a wastewater treatment facility perhaps, and then it could be discharged as clean water somewhere else, or it could be disposed of. Treatment is preferred. Okay, let's look at an actual aquifer, a huge one, extending from South Dakota, Wyoming, down to North Texas. Okay, so we'll look at this aquifer's thickness, precipitation, and water level changes. Some would say this is the most important aquifer in the United States. It's also called the High Plains Aquifer or the Ogallala Aquifer. It provides water for many important agricultural areas of the High Plains. What it is, it's a unconfined aquifer in Cenozoic sediments and sedimentary rocks. So relatively recent stuff. Unconfined kind of puts it at risk, right? There's no impermeable barrier protecting it. But it can also perhaps be recharged with precipitation. All right. But what we have here, elevation and distance out from west to east. Okay, so this is like New Mexico, Texas, Oklahoma. And this is the water table. This is the base of the aquifer. Water levels are dropping in the south, and some parts of it may run dry. Okay, so we'll look at this chart too. This is a volumetric chart. We're seeing pre-development, like before people started using this in a huge amount. The year 2000 and projected for 2050. The idea here is that pumping has gone up. Maybe it'll go down a little bit by 2050. All right. Springs and rivers aren't recharging like they used to. And we're losing water in this aquifer more so over time. Not seeing a whole lot of gains here. Okay, so precipitation helps recharge it because it's unconfined. All right, so the greatest precipitation is up here, and the least precipitation is towards the west. All right, the northern part has the greatest saturated thickness, supply, and then the water table decline is greatest in the south, in Kansas and Texas. Okay, so saturated thickness up here is much better, much more stable as well, because this map is showing us change in the aquifer over time. It's not looking so good as we go further south. This is pre-development to 2013. We're seeing it go down over time. Something to think about. Not only do we need to protect our natural resources from contamination, we also need to think about what overuse and overpumping looks like for a given aquifer. And we'll stop here for this chapter.